Well, welcome everybody to our last methods hour of the winter 2022 term. I'm very sorry that I'm not in East Hall in person today, but Natasha Chaku and Bennett and others are in that space. So it's my distinct pleasure to introduce Bennett today. Before I do, I'll just put a call out that if anyone has ideas for Methods Hour, things they'd like to present, talk about, discuss next academic year, please feel free to reach out to me or go to the Methods Hour website, which I can put in the chat in a second, and talk to us or reach out to us through those means. We'd be happy to explore a presentation with you. But today, and ending winter 2022 on a high note, we have Bennett Fauber. He's a senior applications programmer and analyst at Advanced Research Computing, also known as ARC, here at the University of Michigan. Specifically, he's the Linux system administrator for math and psychology, and practically the person many of us run to when we have a big data problem that needs to be sped up, scaled up, or hopefully made possible. Due in part to this large role he's played in these departments, and also for NII, or the Michigan Neuroimaging Initiative. Bennett received Moore's Research Technical Staff Award in 2017. So we're incredibly fortunate to have him with us today, speaking about computing resources available that's going to help a lot of our work, I suspect. So Bennett, thanks for being here, and please take it away.
Okay, so the title should be pretty obvious. Hopefully it will not turn out to be a lie. This is about computing resources, and it's about data analysis strategies. And it's also to some extent about how you should look at what you do on your computer. So just to give you some idea of who I am, I was an undergraduate student at the University of Washington. I studied medieval history and linguistics. I got out, I started graduate school in comparative literature. I was looking at detective stories in 3 different cultural contexts. That didn't earn a living, and so I ended up coming to the University of Michigan and ran into a bunch of mathematicians, and totally by accident ended up going to graduate school in biostatistics. I didn't finish graduate school. I had enough biostatistics to be roughly the equivalent of the first year of statistics that's taught in the psychology department. That was enough, however, to get me hired as a statistical consultant and statistical software support person at both the University of California, Davis, and at the University of Michigan. At some point, I was getting pressured to get a master's degree in statistics. That sounded really hard. So instead, I became a system administrator and worked on large-scale distributed Unix environment here at the University of Michigan. At one time, we were doing about 2.5 million unique logins per month, and we had about 85,000 users. So I'm used to big things. Then I decided big was too big, so I became a Linux system administrator for the math department, where there were only about 100 people. The psychology department found out that I do Linux, and so they came by and said, please, will you help us too? And then finally, I transferred over to the Advanced Research Computing group. So why did I tell you all that? Well, I'm telling you that all of the stuff I'm going to talk about today can, in fact, be learned by the technically disinclined, of whom I am one. Okay, so hints and advice to sort of remove people's fear of computing. Using computers is mostly about lots of little teeny details. Many of you have cursed the semicolon if you've ever worked with SAS. It can be slow learning difficulties, and it is never as fast as you wish it was. Don't try to learn too many things at once, because this is a great way to send yourself into a fit of frustration. Buy cheap things to throw at the wall when you need to break them. And always be patient with yourself, and especially be patient with others. I found that it's useful to remind myself both to be patient with myself, but also if you're trying to explain it to somebody else, be patient with other people's lack of ability to take the 356 details that are needed and put them in their head all at one time. So I did it. I've learned this stuff, and that's why you should believe me that all of this stuff is possible for you too. So that said, big topic of concern in the last couple of years has been reproducibility. A lot of this has been driven because it's been discovered that there are a number of published studies that when other people go and try to get the same results on their own computers, they were unable to do that. And so it's essentially become very important to make sure that what you do can be done by somebody else and get substantially the same results. I personally would never trust a p-value of 0.048. If it's that close to the wall, I think I would do something different. But in any event, you want something that's substantially the same, right? Numbers may differ from computer to computer. So if you run it on a Mac and you take the same software and you put it on a different computer, maybe even just a different Mac, you might get slightly different results, but big differences are bad. There's a recent technology called containers, the most famous of which probably these days is Docker. And essentially what Docker does is allows you to create the core of a computer and treat it as a single software program. And you can move a container from computer to computer and eliminate a lot of the differences that you would otherwise see because you're carrying more of the software that's computing your results with you when you move the container than you would be if you simply move the software itself. A big part of reproducibility is documentation. And documentation is important to three major audiences. The first is that documentation is really, really helpful to your future self, because I can guarantee you that if you write a complicated piece of R code or a complicated piece of Python and you do not put comments in that file, 6 months from now, when you have to go back and redo it because something didn't come out quite right, you're going to be cursing yourself that you did not write down what it really means in there, okay? The second audience is other people who may need to replicate your work. That could be an RA in your lab. It could be your thesis advisor. It could be somebody who wrote to you because they read an article in the journal. So those are the three people, right? There's yourself, the people in your lab, and those random strangers from the internet. The other thing I'd like to talk about is kind of a preamble before we actually get into the resources that are available here at the University of Michigan, is the difference between personal computing and what I call shared computing. And personal computing lives up to its name. It's very personal. It's just you. You can be as idiosyncratic as you like, and you'll think it's normal. But it's a lot. Shared computing is a lot like shared computing. And think about what it was like the last time you had to share an apartment with somebody and how you felt about dirty dishes that you did not create. So there's a different mindset that you should enter into when you start thinking about reproducible computing and sharing a computer with other people. When we install software on our laptop or on a machine that's in the lab that we're the primary user of, we typically don't think about it. We just do it because we want to get this thing done. That's going to lead to irreproducible. There's a whole journal that you could publish in fact, to the Journal of Irreproducible Results. I don't think it hits highly on the citation index though. The other thing about it is that when you do this on your own computer, many software installations, particularly with open source software installations like Python and R and so on, will make other changes silently to your computer that you don't know about. And they may actually change results in other projects that you have. These are the kinds of things we want to avoid when we're trying to do reproducible results. So if you're in a shared environment and you have a shared set of software that's installed, everybody is now using the same software base. So that means that if you run a subject through a preprocessing stream and the RA comes in and runs the same, you should get the same results, okay? That's the ideal that we're looking for. And I can tell you for right now, Python and R have made many, many things possible. They're cool software, but they have also vastly complicated what it means to share software on a computer because it makes it very, very easy to take what would otherwise be a really good shared software installation and pervert it into your own idiosyncratic Python installation. Okay, so things to think about with shared computing. Will your code, your data, and your results be published? You have a greater responsibility to provide reproducible stuff if other people are going to be reading about it and expect to be able to verify what you're doing, and that's what science is all about. Will others need to understand the problem that you're trying to solve or analyze and be able to reproduce the results? You need documentation, and just like your article explains your experiment, you need documentation and an explanation of why you chose the software you did, how it was installed, and how you ran it. Who's going to work on it? Is it just you? Well, if you're working in a lab, there's a good chance that there may be another graduate student who comes in. Maybe they only come in the year that you're writing your dissertation, but now you have to teach them how to do what you did. Some of the programs that you might be using either or might be writing even as a graduate student or a postdoc are going to need to be run by RAs who are typically relatively untrained. If you're really lucky, they know more than you do, and you have to figure out whether they're pulling the wool over your eyes or not. So what skills are needed to solve the problem? Do they have to learn Python? Do they have to learn R? Are they working on a Linux machine? If you're working on a Macintosh, do they have to learn how to run the compiler, et cetera, et cetera, et cetera? So those are all things to sort of think about when you are thinking about which software you should use in what environment, what you need to write down about how it was made, and so on and so forth. It's always really good to bear in mind that humans make mistakes. And humans can make mistakes that the computer then does over and over and over again at a really rapid rate. And so it's a good idea to figure out what mistakes might be made and to put in things into your workflow, your pipeline, whatever you want to call that part of it, to try to detect the ones that you've already seen. Some of you may remember Donald Rumsfeld. He had a really wonderful thing where he talked about the known knowns, the unknown knowns, the known unknowns, and the unknown unknowns, and everybody made fun of him. But really, it is true. And so as much as we can, we want to build error checking in for the things that we know. And we don't want to be too surprised when things that we never even thought of suddenly turn up and we don't know anything anymore. Okay. And then finally, for every project, you should always ask yourself at the very beginning of the project, what is this thing worth to me anyway? Right? Because you have a limited amount of time and you have a limited amount of effort that you can expend. And if this is a low rent situation and you're not going to get something good out of it, don't spend so much time on it that you let other more important things go by the wayside. So understanding and coming up with a good way to evaluate how good is good enough is sometimes a key skill that you need to build on. So Russ Poldrack should be everybody's at least somewhere in their pantheon of neuroimaging heroes. Did a blog post a while ago. There's a link to it at the end of the slides. Talking to people, especially people who are coming out of graduate school and getting new faculty appointments about what should you ask your future employer, which is assumed at this point to be some kind of a university probably. What should you ask them for in terms of computing resources if you want to analyze MRI images in human subject studies as your primary research area? He identified essentially these categories that are bulleted here. So he said personal computers, if you're by yourself, you just do it all on your own computer. Most people are going to grow out of that relatively rapidly. In this case, the field grew out of them pretty rapidly, and you can't get away with that anymore. Most of the studies that are going to get funded are probably too big to do in your lab. Virtual machines in the cloud. Well, these are essentially the same thing as your laptop. It just doesn't sit in your lap anymore, so you don't get as warm. Your cat can have a good time. But all of the same issues that apply to your laptop probably will apply to the virtual machines in the cloud as well. You can buy a big machine and put it under your desk or one of the benches in the lab, or depending on what your lab is. If it's a behavioral lab, it's a good place. If it's a wet lab, don't put it under the bench. But essentially, it's a private big machine, and it can either be shared or personal depending on how you treat it. So I come back to, you should treat it as a shared machine. But even so, there's going to be limitations to what one computer can do. And so your obvious next solutions are buy another one or buy a bigger one. You run out of options with those two when we start getting to some of these big public access data sets like ABCD. We have 10,000 subjects. Each subject takes about 6 gigabytes of file space. Running FreeSurfer takes about 6.5 hours per subject. So we're already at 65,000 computing hours. That's a lot to ask of a little machine on a floor. You can make your own computing cluster, but then you have to learn how to be a cluster administrator and all of that other stuff. And let's face it, you have better things to do with your time. You don't want to do that unless that's what you would do when you went home anyway. That's not true for most people. And then finally, there are high performance computing centers or high performance clouds. There's all kinds of other possibilities here, some of which we'll talk about later. And I would counsel everybody at this point, when you think about computing services that are offered by your university, you should think of those as being equivalent to, in your mind, as just another cloud provider. So if the university gives you file service, you want to see, you can compare them directly. How much would that much space cost me in Amazon Web Services? How much would it cost me in other things? So there's nothing super magical about buying these things from your own university. Usually it's to your advantage because they're cheaper and the tech support is a little bit better. Okay, so there are other non-monetary reasons to choose as a vendor, your preferred vendor, your own university. And often the rates will be good if you have a grant that's administered by your university as well. So the real choices here as far as computing stuff like hardware and things is what's in your lab, and what's in the cloud. And in this case, I'm gonna be talking mostly about the ARC clusters. So as a reminder, personal computing is a mindset. It's not a machine or a resource. We have lots of people using the cluster who treat it as if it was their laptop. And many of them get in trouble. And then I have to answer their questions. If you're doing this for a class, it's fine. You're going to finish the assignment and chances are that's going to be the end of it and you don't have to worry about it. And your instructor is almost certainly not going to have the time to go and say, well, give me your software and give me your data. I want to make sure this works. Okay, they're going to trust you mostly. For most other kinds of projects, you probably want to take the attitude that what you're doing is going to need to be done by somebody else. And you should plan ahead for it because reconstructing it after the fact will cause you to eat lots of aspirin and have many headaches. So when we talk about a computing environment, what's actually in a computing environment? Storage. And this has become more and more and more and more and more and more important over the last several years as the size and variety of data has grown. When I first started computing, a 10 megabyte hard drive was considered huge. Okay, that's how old I am. You can tell with gray hair. Okay, so the other thing about storage is that if you don't have appropriate storage, it doesn't matter how good your computer is. It's got nothing to work with. And so when you think about storage, you also think about how do I get that storage accessible to the thing that's going to compute whatever it is I need done. The accessibility part. If you have a computer and it's in a locked room and you're the only one that has the key, it's not going to do anybody else any good. If you put it on in the cloud and anybody in the world can get to it, you're not going to be working with private data. So there's two kinds of accessibility there. Who can get onto it? Who shouldn't get onto it? And do we have the right balance of those two? The right people can get on and the wrong people cannot. And that also goes back to storage. Big issues there that I'll deal with. Connectivity. One form of connectivity is to walk into the room, sit in the chair, and start hitting the keyboard. Right? You're connecting with your computer that way. There are 3 people in this room, for those of you who are not. I have no idea how many of you are out there, but you're not here, so you can't touch my keyboard. That means we have to have some other mechanism for you to connect to my computer to be able to use it. Even if you connect, are you going to be able to bring up a graphical desktop so that you can look at a picture of a brain and see, okay, did this registration work out properly or not? Can I see the graph of males versus females in this particular thing? So there's also that kind of connectivity. Do you actually get connected so that you can do with the computer what you need to do with it? And then finally, there's the usability, right? A lot of people use Windows because it's easy. You can move the mouse around, you click on things, stuff happens. It's really cool. You don't have to remember a lot of obscure syntax. Those semicolons don't bite very often. All that good stuff. So when you're thinking about what computing resources are appropriate, you want to think about who's going to be using them. How much are they going to have to learn before they can do anything useful for you? How much are you going to have to learn before you can do anything useful? And will what you have to learn to be able to use that computer be reusable in the future and become a positive benefit to you and other people? Right? It's nice if you can learn skills that when you put them on your resume and apply for that postdoc position, make you go from the short pile or from the tall pile to the short pile of people that they want to talk to. Okay, so storage. Storage is really cool, and it's also a real nightmare. Okay, it's a nightmare because of size. It's a nightmare because of how people organize their files or disorganize their files on the hard drive. It's a nightmare because you have to figure out how to use it on one computer, but oh, no, wait, the other computer is the one that does this. Now I have to get it over from computer A to computer B. Oh, wait a minute, it only works on computer B. Now I have to put it back. Okay, so as I said, without data, no processing or analysis can be done. That's why it's important. I don't think I have to kill that horse anymore. You want to match your storage to your data. Get a storage place that's appropriate for the kind of data that you have. The compute can follow along. Once we know where your data is going to live, we can figure out how to get some computational power nearby. You don't want to pick the computing first and then struggle trying to find a way to get the data over to the computer. This is what I have nightmares. Okay, data regulations. The data use agreement haunts my dreams. It keeps me from sleeping. It's making me retire early. It's all the things that I hate in the world. But it's a fact of life. The regulations surrounding your data and where it can be stored and where it can be analyzed are really complicated, and they're really hard, and there really is not very much help when you need to figure out whether the rules that you've been given are going to be met by the computer you want to work on. If it's your laptop, this gets a lot easier. You know you're going to have to encrypt it. You know you have to have some kind of special login stuff. You know you can't lose it, otherwise you're in big trouble, right? All those things. But another thing to remember is that the IRB reviews your ethics. It does not review the technical setup of the computers you are using, and it does not tell you whether those are sufficient to the data as you propose to use it for ethical considerations. There's a compliance office at the university that will look at your IRB stuff, and then they will look at the federal regulations surrounding things like human subjects and so on and so forth. And they will come back and tell you what the technical requirements of your computers are. So please don't get too frustrated, because it's not going to get you anything. But be aware that it's not just the IRB that's involved here. There are other people. There's also the University of Michigan. They call it the Information Assurance Office, which is just a euphemism for jackbooted security people. Okay. They're the ones who are going to come by and ask you, well, did you do this? Well, did you do that? Well, did the other thing, and so on and so forth. There are lots of people on this campus who, if they find out what you're working on, will want to come and tell you what you have to do to make it properly secure. Look out for them. Okay. And like I said, this is a minefield. Tread carefully. I found a couple of graphics for minefields on the internet, but they were too gross, and so I couldn't include them. So all that ethics and access and stuff aside, some of the now technically kind of things that you might want to be concerned about are, how do you get the data from wherever it's coming from to the computer where you want to work with it? This is true whether your data is generated by yourself or whether you're getting from someplace else. So for example, if you're doing a behavioral study and you have a computer in the lab and you've got some stimuli and they're going to do some reaction stuff, it doesn't matter whether they're saying out loud what their reaction is or hitting a key at a certain speed, you still have to get from the data collection device to the computer where it's working. Same problem is going to apply for the fMRI, right? You have to get it from the MRI lab to wherever you're going to work on it. There are a couple of EEG machines in the basement of East Hall. You have to get it from the EEG machine and the computer it's hooked up to somewhere else. And the two ways that you can do this, basically three ways, except if it's local, only two that matter. The first is with an explicit transfer. So let's say I have an EEG machine. I have somebody come in, I put all the electrodes and grease up their head, and we have them cool things. And then we end up with a bunch of files on our computer. I can either explicitly copy them. You can drag and drop them if it's a Windows machine. You can use a command line version of a copy program, and that would be an explicit transfer. The implicit transfer is where you have a file server. You connect the computer to the file server, and it just looks like any other folder, and you just drag it and off it goes. Okay. An implicit transfer will always be easier and more flexible than an explicit transfer, because you've already done all of the authentication stuff when you start up and log into the machine. If you have an explicit transfer, that's a separate step, and there can be separate complications that go along with it. And then finally, for really large scale data transfer, there's a great XKCD cartoon where he does the calculations about whether the internet is faster than FedEx. And I can tell you that it doesn't matter how fast the internet ever gets, it will never get as fast as FedEx. Okay, so if you've got 60 terabytes of data to move, it may well be easier, both bureaucratically and in terms of time, to copy it to a physical device, put it in a box, and send it to them. It's also, in many ways, a much easier. So bear in mind also that data transfer can take as long as the computation step. Kind of think about it. 60 terabytes of data over a slow internet connection takes how long to copy? Okay, so I'm going to talk about active storage first, and active storage is storage that you can put files on it and then use them with some kind of an analysis program that reads those files, does some good stuff, and puts new files out there. And active storage, your choices are basically your local computer. The simplest thing to do is put the computer on the same, put the data on the same computer as the software that you want to work with it. So that's your local hard drive. It's got a lot of flaws. What happens if somebody spills coffee on it? What happens if there's an electrical surge and the motherboard blows out? Hard drives go bad. The guy in the IT department came down on Tuesday night without telling you and gave you a new computer. Where'd your data go? Okay, portable storage. This is a USB drive. The last time I was actively involved with USB drives was about 4 years ago, and we were seeing about a 30% failure rate within 2 years. So I don't trust them for long-term use. They're perfectly fine, and they're perfectly fine if you already have other copies. But don't think of them as a safe place to put your stuff, okay? We have two file server services at the University of Michigan. One is called My Storage. We actually have three if you include Windows file server stuff. So the Windows file server stuff is great for small files. If you have Word documents, you've got PDFs, you've got PowerPoint presentations, stuff that you're going to take to conferences, a small access database of the subjects that are in your study, things like that would be great on a Windows file server. You're not going to be using those for large scale analyses though. That's also a good place to put anything that's got really strict permission stuff. So if you've got things with your subjects' names in them, put them there because that's where the security is good. Leave the names and the personal details of your subjects behind when you go to large scale analyses. You want to make sure, insofar as possible, that the data that you put out on large scale HPC clusters is de-identified. Okay, so the file servers that are good for de-identified data are this MyStorage. MyStorage is the older of the two services. It's good for small files. The file server that they have is really set up to do a bunch of small files because a lot of what it serves is departmental business. And let's face it, the department secretary is not going to be getting data from ABCD. The other thing about it is cost, because you can get it per gigabyte. So if you need 20 gigabytes, you can get 20 gigabytes. If you need 5 more gigabytes, you can just get 5 more gigabytes. The next one is this turbo storage, which is also a file server. It was set up primarily to deal with big files, which means that it's not very good at doing small files, and vice versa. It also is, because it's large, you can't buy it by gigabyte. You have to buy it by the terabyte. Terabyte is a lot bigger than a gigabyte. Whether it's 1,000 or 1,024 times more, I'm not sure. It depends on who you ask. So this is good. Turbo can be set up to do Windows, Mac, and Linux all at the same time. It's a choice that I don't recommend because it makes dealing with the permissions a lot more complicated. And we have, if it was criminal justice, we would call them recidivists. But repeat people who come back and say, hey, we're having trouble with permissions. Can you help us out? If you make Windows do Windows and Linux do Linux, doing the permissions on either of them is going to be a lot easier than if you're trying to mix and match. Okay, so that's my personal opinion. Other people will say, oh, we've been doing this for years and it works out fine. A lot of it is going to be on a case-by-case basis. And again, it's going to depend on who's working for you and how much they know. So costs. Portable storage, it's pretty cheap. You can get a 2 terabyte hard drive, I think, for $120. So you can store a lot of data on it, right? We already talked about whether it's a good place. The nice thing about it is you can encrypt the whole drive. So if you put data on it and you lose the hard drive, you're kind of mostly okay, right? Because people can't just read it. You're going to have to replace them either for age or because you use them a lot. The MyStorage, you pay monthly. You have to have a short code to be able to get it. So graduate students, you're going to have a benefactor. You could, as I said, you can buy it by the gigabyte. The other nice thing about it is if you need a lot for a short term, you can increase it. And then 3 months later, you can delete the files and tell them to decrease it. So your monthly bill is like your electric bill. If you don't turn your lights on, it's going to be small this month. If you leave them on all time, it's going to be a lot larger. The same essentially is true for Turbo, like I said, except that the units are terabytes. The nice thing about it, though, is that your benefactor can get 10 terabytes of storage for nothing. It's renewed every year. So it's like an allowance that the university is giving researchers now. And if your benefactor is a benevolent benefactor, if that's not redundant, you may be able to get one of those terabytes from them. Okay. Both MyStorage and Turbo Storage can be connected to our clusters as long as they have the Linux capability. One of the first projects that I worked on with folks in the psychology department was to try to set up a backup system, or a backup and an archive system for neuroimaging data that had been collected over the previous probably a decade or so. And one of the first things that we had to do was to clarify the terminology about what's the difference between a second copy of data, a backup of data, and an archive of data. So a second copy is probably the least opaque of the terms. It just means you have a second copy on another place. So if I hit the delete button on computer A and I have a second copy on computer B, it's not as big a catastrophe as if I did not have the second copy. A backup, on the other hand, something that's done by a special piece of software. It's done on a regularly scheduled basis. It's planned, and it keeps track of what your files look like at particular points in time. So that if you need to go back and figure out what a set of files looked like on December 15th, you can do that. That's not the same as a second copy, okay? And then finally, there are archives, and an archive is designed to be long-term storage. You're not going to look at it. It's there in case somebody comes and says, hey, you know that article you wrote in 2001? We'd really like that data. Well, you don't want that on clogging up the hard drive on your current lab machine because you got other things that you've moved on to. But it's nice to have an archive that you can get that data out of to provide to somebody else. Who knows, maybe you'll win a Nobel Prize and you'll want to donate your data and all of your research projects and code to some, library or presidential thingy-magogger. Okay, and so we have a service at the university that will do backups and archives. The backup service is hugely expensive, unfortunately, but the archive is not. Okay, so we'll come back to that. Computing power. As I said at the beginning, what happens when the computer on your desk is not big enough? What do? You buy another computer, you buy a bigger computer. So computing power, how much you're going to need depends on both what you're doing with that computer and how much data you have. So how big does its memory have to be, and who's going to be using it, how many people are going to be using it at the same time. Okay, so regression. Everybody knows about regression analysis. People have been working on how to compute regression analyses since the 50s. No, before that. Regression analysis can be done with a mechanical calculator. It does not require a lot of computing power. Software is specifically written, most regression techniques at any rate, were written back when there wasn't any memory available. And so they're very parsimonious in their use of memory. Mixed models, on the other hand, are not regular regression, and they cannot be calculated in the same way. And they didn't become popular until computers got big enough to be able to do the computations and not like stress everybody out and cost $1 bazillion. So Bayesian techniques, simulation techniques, all of these things are going to require some kind of power or another. There are two kinds of power really that you're going to think about. One is speed. How fast can it do 1,000 operations? And the other is going to be how many operations can it do at the same time? So most of the time, what's going to be you're going to be short on is computing time. Individual calculations themselves can take a little longer as long as you can do more of them at the same time. If I have to do 1,000 operations, one right after another, and they each take a second, that's 1,000 seconds. If I can split those up into a group of 100 and they each run 10 computations and it takes 1.5 seconds, which one finishes sooner? Okay, so that's the basis of parallel programming, and it's also the basis of cluster computing, is that we split things up and they may individually go slower, but in aggregate, they're going to end up all finishing the task faster. So the other is that more often than not, the things that are time consuming aren't particularly computationally demanding, right? So MRI preprocessing is a good example. It can take 24 hours to do like a full preprocessing if you're doing DTI and you've got you want to do free surfer and do some surface analysis, and then you've got to do the voxel based and all of the cleaning and so forth and so on. And that can add up and figure a day each, okay? But it doesn't, you can do that on a computer with 8 GB of memory. It's not a particularly demanding kind of a thing. So that leads us directly into clusters. What is a cluster good for anyway, for crying out loud? Repetitions. If you have the same thing that needs to be done over and over and over again, and it takes a while, where a while, to my mind, a while should be about an hour or longer, but 20 minutes is fine too, especially once you've got it done and you have to do it a long time. So for example, the aforementioned ABCD data set with 10,000 subjects. I'm, I guess, pretty good friends with a guy up in the psychiatry department who's been working on the ABCD data for years now. And there are 10,000 of them. So that's a great thing to put on the cluster. Because once we've figured it out for one subject, we can run it on 10,000 subjects, and it doesn't take a lot of extra effort. All we have to do is submit more jobs. The cluster machines, we do have a few of them that have more memory than any sane person would ever put in a computer that they buy for themselves. We have a computer that has 1.5 terabytes of active memory in it, not disk space, memory. That's pretty big, okay? Most people are using hundreds of gigabytes of memory. Typically, it's over 128, which is about what most workstations these days get, even if you get a really good one. Some are going as high as 256, but 512 gigabytes is not uncommon. It is uncommon for somebody to really need a whole terabyte of memory still. But when word gets out, you need lots of computing time. So what are you going to do with your laptop if you have something you want to run on your laptop and it's going to run for 3 days? You're not going to watch any movies. You're not going to do any email, et cetera, et cetera, et cetera. So, and then the other thing is you can get help with the software that's on the cluster. There are people like me that are paid to answer your question. So Michigan clusters, we have Great Lakes, which is for general use, unrestricted data. We have ARMIS, which is technically for HIPAA data, but if you have other restrictions on your data, it may be appropriate there as well. And then Lighthouse, which is where researchers, essentially, this is the cluster under the desk, except that we're the system administrators. Almost everybody in psychiatry or psychology would be using Great Lakes or occasionally ARMIS. So we have a lot of software already installed, and you can ask us to install things that you think you're missing. The faculty will get free time on it. I think about 80,000 compute hours is free. LSA and engineering students have access to free accounts so that they can do a limited amount of computing without having to pay extra. They can connect to these file servers that I was telling you about. We have a multi-petabyte temporary disk. So if you need to do ABCD, you could download big chunks of the ABCD to our temporary disk, do some stuff with it, and then delete them behind you, okay? And then move on. We also have hundreds of computers that will do work for you instead of 1 or 2. It's got scheduling software so that you can put 1,000 jobs in and it will run them as things become available to do so. And the skill that you learn for using that scheduling software is portable, because most of the national clusters and the clusters that you encounter at other universities will use the same thing. We have a graphical interface so that you can get something that looks like a desktop to do some of the things that you would do on a cluster that you would normally do on your laptop. It's a Linux desktop. We have RStudio, Jupyter, MATLAB, and so forth. We don't have hardware graphics, so you're not going to be doing any fancy visualization. It's not a replacement for a local machine with a good monitor. And then the link is in the slides, which everybody can get to. Not Michigan. So there's an NSF-funded project called Exceed. It's got a new name, but it's essentially the same thing. There are computers out there that have been used to simulate the first seconds of the universe. They're really big. Most of you will not need to use computers like that. There's another thing called the Open Science Grid. Any of you who are working with animal models, this would be a really good idea to look into. For human subjects data, it's a little dicey because of the possible restrictions, because you're dealing with human stuff. contact ARC. So physics, engineering, biology use these a lot. There are millions of compute hours available. Skills that you may want to consider acquiring. If you're going to do serious science, you're going to run into Linux one way or the other, or it's going to run into you. It will be good to know something about it and get a little experience. Git and GitHub. GitHub is a web-based place for Git repositories. It's a great place for sharing software. People have written co-authored books and used Git. It lets you keep track of what previous versions of things look like. Git would be nothing if it weren't for GitHub. GitHub is a great place to put things that you want possible employers to look at as a way of judging your technical capabilities, because they're going to look for you anyway, and you might as well make it look good. Okay. The HPC and Slurm, that's the scheduler I just mentioned a moment ago. Getting some experience with Docker and Singularity, those containers, is also something that's going to be very useful. There are workflow managers. These are things that can monitor the progress of your files throughout a sequence of steps. And then if something goes wrong and it gets interrupted, they can figure out which ones have not completed. They skip over the ones that are already done and then pick up where they're left off. They're great in terms of making the output of your runs predictable. And then finally, programming languages are Python, MATLAB, and JavaScript. If you know those, you can be a hero when you get hired into a lab as a postdoc, and you will also get a lot of extra work. So it's up to you whether those are worth it to each other. And then finally, I have a bunch of links here. The first link is Russ's advice to people getting new appointments and how to ask for their computers. I don't agree with everything, but it's a great place to start. If you want to look at the technical details of how things can differ just because they're being run on a different computer or by a different version of the software, the second reference is Tristan Glattard. He's from up in Quebec. He did a really good paper on illustrating some of the examples. And then finally, looking for control about workflow and so forth and so on, our very own Katie Askren is the lead author on this paper about how to do reproducible neuroimaging and quality assurance. And then finally, the links at the bottom of this page are for the advertising sites for the various services listed. Okay. And then you can contact us generically at arcsupport@umich.edu. Don't be afraid to ask. If we hate you, we'll sell you. Okay, or we'll just tell you that your question is not something that we can do, and we'll try to find somebody who can do it. And then we also have office hours at the Coder Spaces. I'll let you go to the link here, and I'm over time, but that's it. Questions, comments, concerns, etc. Take it away. Should I stop sharing?
Yeah, you can stop sharing.
Hi, Adrian. Where?
Up in the top corner.
Yeah.
In our gallery.
Okay.
All right, great. We can open it up for questions. I can't see in person. If you want to monitor in there, Natasha, and in the chat, or if you have a question here on Zoom, feel free to type it in the chat or just unmute yourself and ask.
Yeah. Or raise your hand or whatever.
Yeah.
Hi, Michael. Hi, Molly.
So I actually have a question. I'm not sure how well you guys all can hear me, but so if you are starting a grant or you're starting a new project, when do you recommend we start thinking about data storage, data computing, and when do we contact you folks at ARC?
I would recommend contacting somebody about what you're going to do with your computing at the point at which you think you have a good idea that's grant worthy. In a lot of ways, we are happier to work with you before you write your grant than after you write your grant. simply because we can anticipate possible problems and we can give you better estimates of what the costs might be like. We can also, if you're ready at the time that you're writing your grant, to think about who might be working on it and what kinds of skills and software and so forth and so on. We can also talk about that. It's really a limit of your imagination, but as a general rule, I would say earlier is better. And it would probably be harder to cut off the details that we give you than it would be to have too few of them.
Great, thank you.
Right? And grants, I mean, let's face it, grants only give you a little teeny section to talk about your computing anyway.
Right.
But you just want to make sure that nothing that you're proposing is actually going to be kind of like impossible. Are you primarily human subjects?
Yeah.
So I've been trying to encourage people for years in your grant when the IRB looks at it to include language in the conditions of use that say, we will do our best to de-identify you, but we may very well put these de-identified images on the open internet for anybody in the universe to look at. Is that okay with you? And say it in that kind of common language so that it's very clear to the IRB that you told these people you plan to publish it on Facebook. Does that make you nervous? Because if you get that kind of okay from the subjects, that means that your data use restrictions later on are going to be lighter. I'm not saying that to give you a license to go and be irresponsible. I'm saying it so that you can be responsible, but have fewer people breathing down your neck and looking over your shoulder. You still want to get sensible advice about keeping things, right? And you don't want anybody to scoop. Right. Any other questions? Here we go. All right. Yes. Are there ethical IRB concerns when using GitHub? GitHub is not usually a good place to put data. And most of the time, what's going into GitHub is going to be documentation and code. And so there won't be privacy considerations about that. You might want to be concerned about copyright and or other people using your stuff before you have a chance to publish it. But GitHub does allow you to have private repositories where you don't give permission to the whole world up front, but it's there so you can do so later once you've already got credit for your hard work and brilliance. And then my career path, okay, so yeah, going from history to statistics to computers, are there things that I did to polish my programming skills? Yes, I sat in an office where people could come and say, I don't know how to do this. How do I do this? And then I had to answer them. I think that's trial by fire experience, on-the-job training. There's all kinds of terms for it. I also, frankly, found there were a few topics that I just found interesting. And I went and tried to do them for myself. And in a couple of cases, especially early on, I had people who came and were asking me questions. And I said, I don't know what you're doing. I want to come and see what your real science is about so that I can understand what your computing is about. And so, for example, I went and in the early 90s, I came over here and worked with a master's degree student who was doing videotapes of people's interactions with other people and then coding them. And that was the basis for what they were doing in computing. I just wanted to see how it worked. I've done similar things. I went over and worked in the wet lab for a cancer study at one point because I wanted to get an idea of how did they collect data and how did they go from test tube to computer tube. I went up and went through the MRI lab up on North Campus to see how that works and standing up there. So curiosity, your first word there, right, is I was curious. The coolest study that I never got a chance to go was studying dolphin whistles. And I thought it would be really cool to be able to get on a boat in Perth, Australia, and go looking in the ocean for dolphins who were singing. And whales, we did whales too. Anybody else? Oh, come on.
Bennett, I actually do have a question related to your comment about de-identifying or the ability to de-identify or not, like fMRI data.
Mhm.
Obviously, you can remove information from like DICOM headers about dates and names and height and weight and that sort of thing. But there's also programs out and available now that deface the MRI or structural or functional MRI images. I guess just curious on your thoughts on how that kind of is that I don't want to say sufficient, but is that a way? Is that a sufficient way or a reasonable way to de-identify MRI or fMRI data, or do you have other thoughts or recommendations?
So couple of things on that. Yes, that is actually the standard practice right now. As far as I know, there is no current standing regulation about putting structural images that are full structural images, including soft tissue, on the internet, right? That's up to you and the IRB and your subjects. But most people who are doing studies do some kind of defacing. There are several different programs that will do it. My best information is that functional images are of sufficiently low quality and large enough voxel size so that defacing isn't even practical. And most of the time when you're working with functional images, you could include the already extracted brain for the published data. And then the full structural or the full functional and structural images would only be available by special request and under a DUA. So those, right, some studies, what they're actually interested in and why they want your data is to figure out how to better get the brain out of the rest of the head. Some of them don't trust how you did it, or at least they want to verify that you did, right? So trust and verify. But so there are alternate mechanisms for those. The biggest problem that I see, and maybe I'm wrong about this, but is to separate out your types of data, because there are the images and the imaging data. And you're right about the DICOM headers. If you do it in a hospital, patient name, and there's other stuff that might be included in there. But most MRI studies are also going to have behavioral data. There are going to be other kinds of things, and that's where all your subject names are. And so if you make it clear in your IRB proposal and in your grant proposal that these data are really of two different kinds and they have different privacy requirements in each other, if you plan ahead to put the stuff that's private under one security protocol and then put the image part, which is got far less possibility of leaking personal and sensitive information out there, under a different and looser protocol, that makes your flexibility for taking the image analysis part somewhere else a lot higher. And by separating them in the IRB, when the computer people come by and say, are you fulfilling your security requirements? You can say yes, because none of the private information is going there. It's only this stuff that we already have pre-approved for the looser rules. That would be true also, EEG data, obviously, we don't have to worry about putting EEG images on them. I think it's going to be a while before we can identify an individual from their EEG waves. Anything else? I know people are bugging out. I hope you all have a good coffee shop to go to. Feel free to get a hold of us if you have questions, so on and so forth. Makes us feel wanted. We consider it job security, all that good stuff.
Well, thank you so much, Bennett. I think this was a great overview and helpful for a lot of folks kind of coming at computing for different types of work and different angles. So really appreciate you sharing all of this with us today.